So welcome to the next lecture of Temporal Logic and Applications. So in the last lecture we have seen temporal logic, how we can represent a properties over time. So we have introduced several temporal operator like next operator, until operator, if operator in future. All those things we have seen, so we will look into more onto that stuff in this lecture as well. Just to have a quick summary or whatever we have seen in the last lecture, let us first try to write some of the queries in the Ctl formula. So so let's say given this tree and we want to express some of the properties, something like this. So from S, the system always makes a request in future. So for if you think of any practical system where you have to express this kind of property, that from a given state it makes a request in future. So always makes a request in future. So if you want to encode this statement in Ctl formula, then what we can write first is something like we will get request definitely. So request in future, so I will have f and this will always hold. So effectively I will get AF request. So that will be my formula for this one. So that is the thing. So now let us look into the next query. So all requests are eventually granted. So all requests are eventually granted. So eventually granted, how we can represent this eventual. So any request that comes will be eventually granted. So this is GR granted, and eventually granted we can ensure that at least in future it will be granted, and any request will lead to this kind of stuff. So if I move on any path, then it should be eventually granted, and all requests are eventually granted. So that means if request comes, then it will be eventually granted, and this means all requests. So this has to be true along all path, and this has to be true in globally. So let us look into another query. So sometimes requests are immediately granted. So sometimes requests are immediately granted. So if we remove, let's say for the time being, the temporal properties, then what we can say, request implies granted, because it will be granted. Now sometimes requests are immediately granted. So immediately granted, and that is sometimes. So it is, if I get a request, then in the next state my grant will hold, and that so it can occur. Sometimes it can actually occur. So this is the stuff, and the whole thing is also occurred sometimes. That means I can say from a given state there will be a state in future. So from a given state there exists a path in future where request implies there exists a next state in which grant is hold. So sometimes that can be translated to sometimes requests are immediately granted. So now let us look into the next query. So in this query it is being asked something like requests are held till grant is received. So requests are held till grant is received. So it's for anytime any request comes, it will be hold till the grant is received. So you can expect that we need this time an until operator. So what we can write, like if I have a request, then request actually implies that request will be hold until the grant is provided. So requests are held till grant is received. That means this should be true along all paths. So request, if a request comes, it has to hold on any path, and this, the whole stuff should hold actually in a global way. So along all path globally, request implies along all path request until grant that should hold. So that we can say requests are held till grant is received. So that is the stuff. So that was the thing, that when we try to model a English language into a formal way. Now the other stuff that we will look into is, given a Kripke structure or given a state machine something like this, we would like to see that what are the properties actually hold here and what properties actually does not hold. So let's say let us look into this one. So if we want to show certain property is true at a particular point, then we have to give a justification why that is true. And if it is a property that starts with E, then one path will be sufficient. That any path originating from a state and there exists a path in which that property is true, I can actually say the whole property is true. And if it is a property true at a given state, then I have to check for all paths starting from that state, and if we can show along all paths that property holds, then we can say that it is actually true. So let us look into this thing here. So let's say if we are trying to look EFR, and let's say we are looking into this state whether the property is true or not. So EFR is, I have one path. If you look into this path, then in this path R is true. So I can say, so from this state there exists a path in which in future R is true. So EFR is true at this state. If you look into this state, in this state EFR will be also true because R is true and the next state R is also true. So eventually I can have EFR is true here. If you look into this state, EFR is also true here because there is a path and R is true. If you choose this path also, still EFR will be true. In fact, EFR is true here as well. Of course, EFR will be true here because R is true at this state, and here EFR is true because R is true at this state, so it can keep on rotating and R will be true. And if you are in this state, then EFR will also be true. So in this scenario, EFR is actually true at every place. Similarly, if you want to check for other queries, you have to look into for every path that whether this is being held or not. Now if we look into AFR, then at this state, in this path FR is true, because in future I have one state in which R is true. If I look into this path, FR is true. So along all path I can claim AFR is actually true. AGS, since S is true at every place, so I can say AGS is true. Now coming to this one, AGEFR is true, or we have to say that whether AGEFR is true. Now when we solve this EFR, we have labeled that in every state EFR is true, and if we replace this EFR, let's say, by X, then X is true at every state. So which is something equivalent to this one, where S here, if I replace S with EFR, then it basically boils down to this equation. So effectively AGEFR is true because EFR is true at all places. P until Q, EP until Q, because I just need to find out at least one path in which PPP and then Q holds. So if you look into this path, then PPQ holds along this path. So EP until Q is true. Now if when we have a query something like this, P until R until Q, what we need to do is we first need to label all the state in which Q is true, and that we can actually find out in this state Q is true, and in this state Q is true. Now what we need to do, I have to look for this part as well, EP until Q, EP until R. Now EP until R will be true, either R is true or from a state where P is true, in the next or in some next state R is true. So what we can do, what we can say, if R is true, then we can say P until R is true. And if I can reach to a state, so similarly R is true here, I can say P until R is true, or more specifically I can say EP until R is true at this state, because R is itself true at that state. Similarly at this state I can say EP until R, because R is true. Now now the thing is, if I can reach to any one of these state and on that state if P is true, then I can also say EP until R is true at this state, and I can reach from this to this, so I can say EP until R is true at this state. EP until R is true at this state, so I can also claim that EP until R is true at this state also. If you look into this one, if you look into this state, then R is true, EP until Q is true. If you come to this state, then here also we can say EP until R is true, because I can reach to that state. Similarly here I can say EP until R is also true, and we know Q is true here. And now the thing is, if I'm looking this query at this state only, then I have a path where EP until R, EP until R followed by Q is true. So I can say this is actually true in the top state. You can verify whether that is true for the other state or not. That I will leave as an exercise for you. Similarly, you can check in the same manner whether something is true or not. This will be actually true, so you can actually work that thing out. Now coming to some of the false properties, like if I want to show some property is not true, then what I have to do, like if it is a property, then I have to choose one path, and on that path I have to show that the property does not hold. So like if I choose AFQ, in that case I can say that if I choose this path, then Q is not true on this path, because from here, from this state I can come to this state, and once I come to this state I will remain here forever. So I will never reach to a state when Q is true. So I have to give one counter example or one path in which the property does not hold if it is a property. Similarly, when I have EGR, like when I try to show this property, then we have to show that in none of the path it actually holds EGR. Like when I have EGR, R holds here, but R does not hold here. So globally R does not hold. So R is true, R will remain globally here, but at this state R will not hold because R is not true at this state. So we can say EGR is not true. In the same way, or in a similar manner, you have to check whether something is true or not. Let's say we would like to see this stuff, AGEFP. So along all path globally EFP is true. So that means what I need to do, so this actually falls in the similar to this one, and if I replace EFP with say S, then it falls to something similar to that one, and we have seen that will be true if S is true in all the states. Similarly, EFP is true in all the state. So now the thing is, we have to check whether EFP is true in all the state or not. So the thing is, if I look into this state, EFP is not true. If I look into this state, EFP is actually true, because I can P is true at that state. So from that state there exists a path. if you and if you look into this part, EFP is true. Similarly, if you look into all these state, EFP will be actually true. And along all path globally, so in this side, in all state, EFP will be true. In all state, EFP will be true, because I have some path in which I can reach to reach to a state where P is true. Fine. Now the thing is, EFP is not true at this state. So along all path globally, EFP, whether it is true or not, because if I choose this path, EFP is not true. So therefore this property will not hold in this state. Similarly, you can work out for this one. I will skip for the time being. Now in order to do model checking, what we need to do is we have to check a given formula. We have to check a given formula F whether it holds on a given Kripke structure M or not, and we represent that M models F. This we pronounce as models. That means F is hold on M, or the Kripke structure on the machine M actually satisfy property F, models F. So we have seen that there will be different combinations of the formulas. We can have a properties something like AU, EU, AG, EG, AF, EF kind of stuff, and also we can have AX, EX. Now so for every type of formula we have to have a method through which we can actually check whether something is true or not. And the interesting thing is that if we only develop rules or methodologies only for these three properties, then we'll be able to solve the other one. So why? Because the thing is, P until Q, when we have this until property, we can represent also as a property as well, because true until some P is nothing but so this is equivalent to a property. A P is equivalent to this thing. And so our claim is that if we can write or if we can develop model checking algorithm only for these three properties, will be done. Now then the question is, then how will you check the A properties? Now in order to check the A properties, we can use the dual that we have seen in the last lecture, like Ape and G are the dual to each other, and we have seen that stuff in the previous class. So what we can do, if I have a property like AF, that can be written as not E, G, not F. So along all path in future, F is true, which is effectively means there does not exist a single path there does not exist a single path in which globally not f is true. Similarly, we can express AGF along all paths globally f is true, which effectively means that there does not exist a single path in which in future not f is true. And I leave this thing as an exercise just to understand that when I have until operator and it is AU operator, like always f until g, then that can also be represented in this form. So I will leave it as an exercise to understand that this is actually hold and this is true. So the thing is, what we need to do effectively, like for a given formula f, we have to verify whether it holds on M or not, and this f can be any formula, and we'll be developing only algorithm only for these three properties. So the basic stuff, we'll start with exf. So that means so this means that exists a path in next state f is true. So if I have been given a Kripke structure with set of nodes, some interconnectivity among those nodes, this will be somewhat with a directed edge. For the time being, I am just drawing it with without any direction, just to give you an understanding. Let's say f is true here, f is true here, and let's say these are my direction for the time being. Now exf means if I look into a state, if I am at state and if there is a state in which f is true, then I can definitely say that exf is true at that state. There can be another path where f does not hold. Fine, but if f is true in this state, then if there is a path from this state to this state and then I can claim exf is true. So that is the stuff that we have mentioned here. So what I need to do, I have to find out the set of state in which f is true, and then I have to look into the set of states, the states. So this state I am referring as S in this example. Sorry. So if I call this state as S in which f is true, and from the transition relation, so this transition relation basically represent kind of present state and the next state relation. So if this is S, I would like to find out a present state from where I can reach to S, and if I from a state T, if I can reach to S, then I can actually claim that exf is true in this state as well, because in the next step I can reach to a state where f is true. So that is the stuff that we are doing. So we are trying to find out a state T, and T2 is, it belongs to the transition relation. Then LT, the level of the T, will be enhanced with exf properties as well. So whatever level was there on this state, that will there we will add exf as well. So that is to check for exf. Now we can extend the idea for Egp properties as well. The idea here is similar to the previous one. So earlier we are just going back only one step. Now we have to go back more number of steps. So what we have to do when we would like to check Egp, so I will look into the set of states where actually P is true, and I am representing as a set that in this state P is true. Or maybe instead of saying P, we can this is P and this F are the same, so better to say Egp is true. So these are the states in which P is true. Now if there is a path from another state to reach to this state, then we know that we can actually label this as exp. exp. Here also we can label with exp. And if P is true in this state, then we know that here Egp is true because P is true at that state. Now if Egp, so the state in which where P is true, effectively Egp is also true there. And if I can reach to such an state in one step, then I can say that Egp is true also in this state. Because if P is true in this state, in all the state we can actually claim that Egp is true on those state. And from any state outside this set of state F0, if I can reach to any one of the state available here, then on that state Egp will be also true. So effectively we will broaden our horizon and we will get a bigger chunk of the set, which will be the new set of states where Egp is true. And we will keep on doing so till we reach a fixed point. And we will reach a fixed point because there are finite number of states. So at some point of time we will exhaust all the set of states and it will reach to a fixed point. So this is the stuff. So this is started with P, and then we looked into the set of state in which P is true, and in one step we can reach to P, and then in another steps we can reach into that kind of states, and we can keep on doing so. And while doing so, we will reach a fixed point which is known as least fixed point. And once we reach to that fixed point, then we know that no further state can be explored in which Egp is true. So how we do this so this idea is being has to be implemented in an algorithmic way, and once we do that stuff we get the set of states in which Egp is actually true. So the idea is similar to the previous one. I actually start with the set of states where P is true. So for all state S, wherever this S belongs to the set of state in which SP is true, this is the set of state in which SP is true, we label those states with Egp is true. And then we choose one of the state from this set, we remove, and we then keep on iterating. So again we proceed in the same manner, like Egp is true in this state, then we try to find out its predecessor T such that in this state is not already labeled with EFP, then if it is not labeled with EFP, then we label this one as EFP. And again, once we label this one as EFP, then we have to explore its predecessor, because there can be another state from where we can reach to this state, and if it is the case, then we have to update this state also with EFP. So we add this new state in SP as well, because this SP is eventually basically represent the set of states in which in future P will be true. So let us take a look into this example. So we have this thing EFP, and this is A XOR C and A XOR B, and let me call this as property P. Now initially SP is empty set, nothing is we do not know anything. Now we have to check in the set of states in which the set of states that models the property G. So first of all, what we need to do is we need to check the set of states in which my P is true. So P is this expression, so I have to find out the set of states in which P is actually true. And what we find that SP is true, or this expression is true at S4. So S4 is so the way we have defined this is P. So P is true in this state, and the overall formula is EFP. So S4 can be marked with EFP because this holds on S4 state. So S4 will be marked with that S4 actually models G. Now what we have to do, we have to look back so what we have to do is now we have to look back we have to see sorry, I made a mistake. So this S5 is actually also models your property P, the stuff that we have written here. So these two state actually models G that we can initially say. So this A XOR C and A XOR B will be true at S4 and S5. So SP is S4 and S5. So that is the initial thing. Now what we need to do is we have to do we have to explore the predecessor of the stuff. Now we choose S4 initially, and S4 has a predecessor S6, and then we can actually claim that S6 will also model G, because this is the EFP property and I can reach to a state where G is true. So EFP is true, so effectively G is true at that state. Fine, so S6 will also model G, and S6 will get added in the SP. Now from again we have to choose one state, and we choose S5, and for this node there is no predecessor, so you do not have to explore anything for S5. Now we left with S6. We have to select S6, and when we select S6 we have to look into its parent, and when we look into its parent then we get S7. So S7 will also model G and S7 will get added in SP. So again then we have to check for S7, and S7 has a predecessor S5 which is already labeled, so we do not have to do any other thing. So we can stop then, and we can say only this set of states actually model G. Now coming to Egp properties, so which is somewhat similar to EFP but with a little bit difference. Like when we have EFP, when we have P, we started with this kind of stuff, we keeps on increasing or broaden our horizon kind of stuff. In EGP it will be the reverse. So in EGP, in all the state P has to be true. So so at least the state I am looking for in which P has to be true, because globally P is true, and there should be a path in which in every state P has to be true. So therefore it will be the set of states in which P is true and maybe less than that. So I start looking into the set of states where P is true. Only a subset of this state can be a case where EGP will actually hold. For example, just try to give you, let's say I have a state P holds here, I have a state P holds here, and let's say and not P holds here. Now if I look into this state, P is true, but I cannot say exist a path EGP is true, because if I choose a path from here, then on this path EGP is not true, though P is true here, but P is not true at this place. So effectively it will be the set of states it will be the set of states it will be the set of state so at most that set in which P is true, and it will be less than that. So what we need to do, we have to look into the set of states in which P is true, then we have to reduce, we have to shrink the state. So what is the idea? The idea is P is true and in the next state also P is true. So I have to keep on checking in that way. So P is true initially, and in the next state P is also true, that we have to check. So we have to keep on repeating the similar stuff, and eventually we will reach another fixed point where which is known as the greatest fixed point. And once we reach to this state, so if I select any state from here, then P is true, in the next state P will be true. So whatever I choose, whatever node I choose, P will hold eventually. So from any path to any other node, P will always hold. So in order to determine this set, what we need to do is we need to find out the strongly connected component. The strongly connected component of a graph is for a directed graph, because the Kripke structure that we have, let's say this is a Kripke structure, and there can be many other nodes, other edges. So now if you look into this one, the strongly connected component says that two nodes U and V will said to be connected if there is a path from U to V and there is a path from V to U as well. Now if you look into this one, if I choose this node and if I choose this node, then there is a path here, then there is a path here, and so this is one path, the other path is this one. So if you look into this way, then these two nodes are connected. Similarly, if you choose this node and this node, you will find only this is connected, but you will not get any path from this to this node. So there is no path. And if you analyze this graph, then you will find that these three nodes are connected with this definition, and these four nodes are connected with this definition. So this is called, this node is one of the strongly connected component. So this is known as strongly connected component. So this is one strongly connected component, this is one strongly connected component, and so on and so forth. So the idea of this algorithm is as follows. So you have to first find out the strongly connected component of what, in which P is true. So I will first find out the set of states in which P is true, and using those states I will try to find out the strongly connected component of those nodes only. Once we find out those strongly connected component that and in which P is true, then I know Egp is true on those states. Now what I have to do, once we find out the strongly connected component of where P is true, then I have to check if there is any other node where P is true and there is a path to a node where Egp is true. Similarly, there may be another path where P is true and Egp, and this path actually leads to one of the strongly connected component. So I keep on iterating the step. So once we find out the strongly connected component, we again go ahead in that manner, something similar stuff that we have done in EFP, with a restriction that there we are looking into any nodes. Now we have to check for every node P is true. So if we know all these nodes are S, then we try to find out node T, and T should belong, T is member of SP, that means where the P is true, and if it is not already labeled with Egp, then we label that stuff with the new properties like Egp. So in this way we can actually continue. So this is an example like EGB. So we have to find out the set of states in which B is true. So we find this is 0, S1, S2 and S4 will be true, in which B is true. So fine. Now what we have to do, we have to find out the strongly connected component. So if you look into this graph, only these four nodes, then you can easily understand only this part of the chunk form a strongly connected component. So this is our strongly connected component. Now what we have to do, we have to take a node and we have to do a revert step. So we start with these two nodes, S0, S2, then we try to find out the nodes in which B is true and we can reach to one of these node. So we choose S0 and then what we do, we try to see whether S0 can be reached from any other node where B is true. So this is the state where B is true and it can reach to S0. This node will not be selected because I can reach to this node but B is not true. So S4 will be selected. So S4 will definitely model G and then we have to select S2. For S2 there is nothing to explore because S0 is already there, so nothing to explore. Now we are left with S4, and for S4 the predecessor is S6 but B is not true, so S6 will not be satisfied, and S1 is the children of S4, so that will also be not explored. So there is nothing to explore any further, so R will become empty and we can actually stop at that point of time. So effectively these three states will be satisfy your EGB. Now for P until Q, it is similar to F P, only difference is that we start with the set of nodes where Q is true, and then we expand our horizon with the set of states where P is true, and from here to here, and there is a state when I can reach from P this state to this state. So that means in this path P until Q is true. So I start with Q and then I broaden my horizon with the set of states where P is actually true. Then whole of this chunk, I know that E P until Q is true, and I will try to broaden my horizon again where again P is true and it reach to any one of those states. So and we keep on doing so in that manner. So eventually we will reach to a fixed point. So it's similar to Egp properties, only difference is that we have to do a logical AND, or we have to enforce that P is true all the previous states, and in the same manner we have to write, and it will be a little bit more involved because you are looking into one of the different condition in this case. Now coming to nested Ctl query, like some of the example we have seen AGEP. So if we have a query something like this, and if you want to check whether this is true or not, then it's very difficult to analyze. So what we need to do, we had to break it up into smaller subqueries. So what we will do, we first try to find out the set of states in which AG not Q is true, and if we know this one, if we can find out the set of states in which this is true, and we can check on all those states P is true or not, then we can replace the innermost part with a simple thing. Let's say instead of I can say this is S. So effectively I have to check EFS properties, where S is this complex Ctl formula. So in order to do that, what we do, we just take it for the time. What we try to do, we try to find out the set of states in which this is true. Again, this is more involved. So we try to find out the set of states in which P is true, and we try to find out the set of states in which AG not Q is true. And in order to do that, we find out the set of states P is true. So here we go back, so we know the set of states in which P is true, and we have to find out the set of states in which AG not Q is true, and then we have to take an intersection of those two sets. In order to find AG not Q, what we need to do, we have to find out first this set of states AG not Q. AG not Q, so we just first look into the set of states in which not Q is true. If I know that AG not Q is true, then we if we know the set of states in which not Q is true, then we can actually answer this query AG not Q. So effectively, once we know this, we can find out the solution for this one. And once we have this stuff, so this will give me the set of states in which AG not Q is true. And if we go back one more steps, then we have to take the intersection of these two sets. And so now all the set of states will be marked with these properties, and then we can apply the normal Egp properties to find out the solution for the original one. So this is the logical AND that we have to take intersection, and once we have the set of states marked with this property, then we can go back and we can find out the set of states in which this is true. Now just to summarize quickly, and some extension of this one, like sometimes we have to specify the properties with some kind of a with a time restriction. So you have to precisely tell that within 4th cycle or some kind of a response time we have to specify for correct operation. And if it is a safety critical systems like aircraft or industrial machinery, then we have to say that within 4 clock cycle or within 10 clock cycle something should happen. So what we need to do is we need to augment this logic with some extra information, because event like if we have let's say event P will happen within at most n time units, then I have to specify something like this. So either P or XP or XXP, or I have to append X n number of times, and then I can say it is P. So which is pretty difficult to write. So what we do is we basically augment the temporal operator with a kind of a bound. That means like P always holds between mth and nth time steps. So in this case it's a global property. Global actually may specify that the property holds at every time point. So here the meaning is between m and n this will actually hold. Similarly for Egp property, it will eventually hold between these two time steps. So any state in between these two will be sufficient. If we have xmp, that means P holds at the mth time steps, and similarly on so on. So Q eventually holds between mth and nth time steps, and P holds until that point of time. So we are basically just extending this stuff. will not go into the algorithm for this one, but just to give you an understanding what does it actually mean. So G24P will basically means that P has to be true here, P has to be true here, P has to be true here. F24P means in any one of these three states P has to be true. X3P means at third time step P has to be true. P until Q 24, P until 24Q means Q has to be true between 2 and 4, and once Q holds, then up to that time point P must hold. So in this state P actually holds. And we can write more complex queries like whenever request is recorded, grant should take place within 4 time units. So here we just use another notation like passage, like when I record a request, the request line I want to specify the pause age. So whenever this passage implies that AF04, so whenever this request is recorded, that means the grant should take place within 4 time unit. So along all path in future within the 4 time units it has to be true. And similarly we can specify the other kind of stuff. So like the arbiter will provide exactly 64 time units to high priority user in each grant. So passage of HP using implies A not of negage HP using, and exactly at 64th cycle there will be a negage of HP using. So this way we can actually extend the stub. So with this I will summarize. With this I will stop now, just to give you a quick summary. What we have done today is we have looked into some of the examples of CTL, how we can convert the English language into the formal properties, and given a properties how we can actually verify. We have seen in an informal manner, we have seen with the formal manner also how to check whether a given formula is true or not. And finally we have seen how we can extend it for real-time properties, where we have to specify the time bounds in the queries. So these are pretty much involved, and if you are interested you can look into those papers and you can understand how real-time properties can be verified in the similar manner, in a variant manner. So with this I will stop now. Thank you very much.